let's get started. Looks like it is recording. Let's finish up these slides on risks and bugs. And so we learned about horrible things. You wrote an essay about one of those horrible things. And we kind of discovered or determined at the end of the day that testing is one very powerful way to ensure that your code is correct, for some definition of correct, and that you can trust it more than you used to be able to. Okay, so we wrote a program, we wrote a test for that program, and that is one strong way for making your programs correct for test. You want to test them with a bunch of different inputs that hit all of your corner cases, make sure to try every line of code, it's all getting executed one way or another. So that's a good way to think about it. All right, so let's write programs and tests. That's one way to gain some confidence in your code, and that's the most common way in industry of testing your programs. There are, though, some cool things that I want to at least tell you about. There are ways to make software that is just correct from the beginning. You don't even need any tests. It's defined to be correct. So let me show you those. There are certain ways to do it. So the first idea is to make maybe 2 copies of the same program, redundant programs. This is very common in airplanes, for example. You have 2 versions of the flight control software running at the same time, and hopefully they agree. And so that each program checks each other's output. They should all be telling the plane to do the same task. And that's one way to ensure that everything is going correctly. You have a bunch of different teams of programmers writing 3 or 5 versions of the same software, and they all have to agree on what it should be. And so that's one way to ensure that it is correct for some definition of correct. And then also, once you get to maybe CSCI 26, if you go that far, you can write a formal mathematical proof about your program. You can reason about your program and say, this is going to do this thing exactly, and you don't even need tests at that point because you've proven formally, beyond a shadow of a doubt, that your program is going to do the right thing. Right? So that's one way to do it. So a proof. Here's an idea of a proof. Here are 2 lines of Python code, x equals 42, and then x equals x plus 1, so just manipulating variables. You can pretty much prove, right? It's pretty easy for these 2 lines to show, after this line, x is set to 42, and then assuming all that, what must be true after these 2 lines? X is 43, right? X is 43 here. And so this idea that I think you have in your mind of how you would prove that can be expanded upon to large, arbitrarily sized programs. And you can prove that, all right, the output is going to be within this range, things like that. And so you can prove mathematically your programs that are, you can prove that they are correct. That is beautiful. That's what we'd like to have. A middle of the road idea is called an analyzer. This is something that I studied in grad school. You can make a program analysis tool that looks at a program, maybe you don't trust it, and it will run that program maybe mathematically to discover properties about it. The output is going to be within this range. Your secret password is never going to be given to the print function, stuff like that. That's something that an analyzer can do, and you don't even need to show anything about it. It's going to be always working out. Okay, and so that's an analysis tool. You usually use a proof, right? You prove that your analyzer is correct, and so these kind of go hand in hand. But these are just high-level ideas that I want you to have seen once. Alternatively, you can make what's called specification of what your program should do. You have these requirements that are given to you by your boss or the government or something, and you can describe exactly what your program should be doing, the relationship between the inputs and the outputs, and then there's a way to verify that your program matches its specification. So there are whole specification programming languages. One is called Z because it was made by non-Americans. That's how they pronounce their Z letter. So you can have a list of requirements, and you'd specify all of those. All right, requirement. Maybe this is your requirement for your program, and you write this down formally somewhere. You can prove it. You can get it out of an analyzer. One way or another, you have to know what you want at the start. Okay, so that's a hard problem to solve in itself. So here's maybe an example requirement. The output of this program should always be greater than or equal to 42. That is a valid requirement that you might want your program to have. And now you could go off, send it, prove that that's going to be true, send it off to an analyzer that will show that it's true, write this in a specification, have it automatically shown. All of these ideas work, okay? But yeah, at the end of the day, you who is making this program or who is like trying to make sure it's all correct, you have to say what it means to be correct. And you can make mistakes in that idea, right? Maybe you accidentally say the program should always be greater than like 12, and that was an incorrect specification. So you can mess up at the specification at the requirement level now. So it's very hard to say, to describe exactly what your program should do or could do. Because if you prove that it meets your incorrect specification, the program is wrong, right? So these are just high-level ideas, very vague, but are there any questions about them? These are ways that people write software that is correct from the start. And so one very popular way to prove programs correct is to use this French program called Cook, I guess if you pronounce it, with the French accent. It's a proof assistant. Very cool. I used it during my grad school years. So yeah, watch out for your specifications because they could be wrong. Maybe it should have been 42, but you wrote 12, right? So that's one idea. And yeah, one very good example of where you want programs to very much be correct is when they're on a plane and that plane is flying you somewhere. Okay, so here is a story from your textbook about air traffic controllers and a piece of software that was written for planes. So there was this cool thing, it still exists, it's called the Traffic Collision Avoidance System, or I guess TCAS for short. What it can do is, like, you have two planes, they're flying in the air, and they have little beacons on them, of course, and they all are required, I guess, to have this little TCAS box in them. And what this traffic collision avoidance system does is it says, it tries to notice, like, given the direction and the speed and the altitude of these planes, it can figure out if they're like about to hit each other, and if they are about to hit each other, if it thinks that there's a problem, this avoidance system, this automated thing, this computer in each of these planes can say, like, all right, this guy go up, increase altitude, this guy decrease altitude, or maybe turn left, turn right, things like that. So it can tell pilots how to avoid a potential collision, which is really nice. But the sad story is this was kind of the traffic collision avoidance system that cried wolf. At the very beginning of time, like when this first came out, it gave off a bunch of false alarms, and so it was telling planes that were way far apart from each other that they were about to hit each other. And so even though this is a good thing to have, a lot of pilots started ignoring the warnings because they're like, I know my plane, I'm not going to hit anybody, I'm so far away. But eventually, like, they worked the kinks out of the system, and it became very, very accurate, and it was awesome. But you still had these pilots who didn't trust it. So unfortunately, a collision in the air happened when one pilot followed the TCAS system, telling it to do one thing, and the other one ignored it and listened to the air traffic controller, so a human telling them what to do to avoid each other. And so maybe the pilot was told by the system to increase altitude, and the other pilot was told by the system to decrease altitude, but the air traffic controller was saying, no, you go up too, something like that. And so unfortunately they collided because of that, and nowadays the software is correct, everybody loves it, and everyone is required to disobey the human now. The software is so important and considered to be so correct. Everybody's required to disobey the air traffic controller and trust the system, follow the TCAS system's requirements before any other human, because they are the ones that take priority now. Okay, that's an interesting idea. You cannot, like, you're supposed to trust the computer over a human nowadays for certain things. Any questions, comments about that? And so this leads to an interesting question that we've been building up to, and I'd like to hear your responses to it, at least in word form. So here's my question to you. Like, this idea, it's like we are trusting this system with our lives now. Do we depend on computers too much? Let's ask each other this question. So please get into your peer instruction groups. Go to the written ice page, which I will clear out. I'll give you a few minutes to come up with some ideas with the people sitting next to you. But let me clear it out here. And what I want to hear is just that. What do you think? Do we depend on computers too much? I do want you to like think in the opposite way. So please try to write one good argument for saying like, yes, we do depend on computers too much, and one good argument against saying no. Maybe we could use computers even more in our lives, and we have not used them too much at all just yet. Okay. So any questions about the question? Please go forth and put your critical thinking caps on. I'll give you a few minutes to type a response, and then we'll discuss. Maybe I'll set a 4-minute timer. Take another minute to get something in there, then we will discuss. All right, let's take a look. See what we're thinking. All right. Yeah. There's a computer everywhere. Maybe that's saying that like if something went wrong, then we are forced to use a computer to solve our problems, and maybe if the power goes out or something, then it's a bad thing. Why we don't rely on computers. So we need human interference to function. Yeah, we need to talk to humans just to be good to ourselves. Let's take a look at group 34. Thank you for submitting those of you. I think some of us are still working on it. So we do rely on computers too much because they have been, we've just been using them more and more. We've gotten used to it, I guess. That's a good way of saying it. They can do the computation. That's what we invented computers to do. They can do all the math for us. And we definitely like that. And we want to keep them around because of it. Let's see what else. We don't depend on them too much. Humans are able to think functionally and apply more realistic solutions. That's true. There are some things that humans are better at. There are some, like art, things like that. There are some things that you can't really teach a computer to do very well yet, and that is going to, like, the essence of humanity, I guess. You can't give that to a computer. Yeah, I like it. So thank you for thinking about it. Maybe some of us are still typing and thinking, but thank you for those who did submit. Let us keep on trucking. Here are my ideas, I guess. We can talk about those. Do we depend on computers too much? I guess maybe like the air traffic controller example kind of indicates that we should depend on them more because they're going to save our lives. They were meant to help us a lot of the time. But of course we have the Therac 25 that kind of ruins the party for us as well. But one good thing we can do is just to get more experience with it is let's go back to our boys and ask them, like, hey Kant, hey Mill, what would you guys think? So Kant might ask the question, should we always look towards computers when we have a problem? Maybe it can solve it. And I think Kant, again, is big on individual freedom. So he would say, like, if you don't want to use the computer to solve your problem, nobody is forcing you to do so. So maybe Kant would say no. Maybe he would say yes if he weighed the decision. And then Mill would definitely try and determine, hey, which one's better? What's going to give us more utility? I think just in sum, like if you combine together all the potential utility of using computers for our lives, I think Mill would totally say, a utilitarian would always say yes. I think computers are better. We should keep them around. They're going to make our lives better. Okay? Any questions about that? Comments? Ideas? Yeah, one big thing is safety. So just to spell all that out, like computers are making us safer in so many different ways, right? Inside of our cars, like we have a little mini computer that runs our brakes so that they never lock up, the ABS devices, right? We have those check engine lights that didn't used to exist. They are able to tell the mechanic exactly what is wrong, and so they can fix it and make sure our car doesn't blow up on us one day. So airplanes, they have the TCOS system, autopilot, so that like on your long flights, your pilots aren't getting tired, all that kind of stuff. Everybody's big on like home security cameras now that are connected to the internet, and that gives you a better, like that makes you feel safer in your home. That's I think interesting. And then before that, I guess you had to buy a bunch of dogs, and that's how you felt safe. You had guard dogs or something. We do have a lot of new things. Like we used to put information in safes, but now we have phones with our information on them, and maybe have passcodes that lock that up, but maybe those could be hacked and broken into. So that's another idea to think about. We're bringing sensitive information with us all the time, and maybe that's a good thing or a bad thing. Who knows? It's quite nice to not have to go physically into a bank and get a bank statement and see like how much is in our account. That didn't used to be a thing before the internet, right? A lot of security behind that. And so we have like two-factor authentication, HTTPS when we're connecting to websites on like a public internet. So it's all there. It's all helping us, I think, though I am biased as a computer science teacher. So this is why I want to get you guys thinking about all this stuff. So I think that's everything that I wanted to talk about for this set of slides. Risks that come with using a computer. Any questions about any of that before I switch gears to something else? Because I said that computers, like, they're not able to think like humans, but maybe they will be soon. So we need to talk about artificial intelligence. So let's get there. And of course, what that means is computers trying to mimic human brains, trying to be smart in some way, to model the way a human might think about things. And that's going to take a lot of processing power. And so the first thing we should talk about is this thing called Moore's Law, which will answer this question. How fast are computers getting faster? Because if we have strong, powerful computers, and we link them up, they can think better, think more quickly than computers like that were built a decade ago. So computers are getting faster still. How fast are they getting faster? Because maybe that's going to help us. The more they can do, the better they can help us, I guess is the right way to think about it. And so this thing called Moore's Law, which came out way back in the day, maybe I think the 60s or 70s, is kind of a model for how fast computers have been increasing in power. It's still pretty much holding, but I think we've kind of flatlined. So let me talk about this. This thing called Moore's Law, it's not like a real mathematical principle or anything. It was just an observation made by Gordon Moore, who was the co-founder of Intel. Very, very famous person. He noticed that the number of transistors in a computer chip, so like in a CPU, was tending to double every about 2 years because they were making them smaller and smaller. They're finding better ways to pack them together. And so, I guess at the start, let's say, our computers were running at like 1 time speed. Then like a year later, they were running at 2 times the speed. Then a year after that, they were running at 4 times the speed. Then 8 times. Like it was, let me draw this better. Maybe here's 2. Then we have like 4 up here, then 8 up here. 1, 2, 4, 8. It was an exponential increase that he saw. Like, you just wait another 2 years, your computer is going to have twice as many transistors in it. That's what he thought. And the number of transistors, more or less, for a very long time, translated to the speed of your computer. So it can do a bunch of calculations very quickly. That's measured in gigahertz nowadays. Maybe you have like a 4 gigahertz computer. Maybe that's what these processors on these giant machines have. So that's how many instructions can be performed by your computer per second. This is like 4 billion nowadays. And with the doubling of transistors, essentially came the doubling of processor speed, which is really nice. For a while, our computers got twice as fast every 2 years as we packed more transistors into them. So that was nice. But sadly, we've made transistors so small nowadays that we're running into power limits and heat dissipation issues. So we have physical problems with making our computers any faster, but we're still trying to shrink the transistors pretty well. So, yeah. 4 gigahertz processors, they were around in the early 2000s, more or less. It just takes a lot of power to make a 4 gigahertz processor. And it needs a really huge heat sink as well, because it generates a lot of heat to make a processor run this quickly. And so, sadly, we've kind of hit a wall in terms of processor speed. And so what did people do? How did they solve this problem? They started making multiple cores per processor chip. And that led to the multi-core era, which we live in right now. And so instead of making like an 8 gigahertz processor, which is going to burn your house down, they started putting a bunch of little processors inside of a big one. So like a 4-core processor, which is made up of 4 little chips. And maybe each of them run at 2.5 gigahertz. But they can each run at once. They're like mini CPUs inside of your big CPU. Okay? And so multi-core is how the world works these days. And though we can't increase processor speed anymore due to these problems, we've still more or less been able to increase the number of transistors on a chip. So that's pretty nice. Moore's Law is still working for now, but we're about to make them so small, like they're getting so small that there are quantum effects inside of our transistors. Like they can only hold on to so many individual electrons at once, and then they can bounce around. So I'm not a physicist, but that's essentially the problem that's happening right now. Transistors, they're becoming so small that they're running into quantum issues, and so they can't really be much smaller. And so we're about to hit a wall soon, and Moore's Law is no longer going to work, but for so long, this is what's happened. So here's a very cool graph that I stole from the Wikipedia page, I think, and you can see this is this is time on the bottom, so like 1970s on the left, 2018s on the right, and then this is transistor count on a log scale, though. So this is a logarithmic scale. Every unit is a doubling of size. So if you see a straight line, as we do, this means that it is an exponential increase, and this is just kind of showing how Moore's law is working out. So yeah, let me just show you some cool facts. Back in the day, the early Intel processors, they had about like 5,000-ish transistors. This is back in the early 70s. And then the Motorola 6800 came out. That was key in Apple computers, and also a lot of early video game consoles. Again, on the order of like 5,000 transistors. Okay, but a couple years later, we started following this law, and then like fast forward a decade, the new Intel processors, the 8086, which like led to our current Intel style processors, had about 50,000 transistors. So getting bigger, everything's getting fancier, more transistors, faster speed, and then you see some outliers around here. You see how the transistors weren't as big as they could have been at that same period in time. These are our ARM processors. They exist inside of our phones these days. If you have a Raspberry Pi, it's in those. ARM was meant to be a competitor to Intel, and it was running at the same speed, doing all the same stuff, but it was a simpler device. It had fewer transistors. So that's a cool historical note. You didn't need as many transistors to do the same amount of things. It was RISC versus CISC, if you've taken CSCI 45. That's a problem. And then, yeah, fast forward some more. You have the Pentium processors, which were huge back in the day. So that's the early 90s. And we were starting to get into the millions of transistors. So that's quite a lot. Computers going very fast because of it. And yeah, still following Moore's law. Still being able to double these things. You can see around here, around the early 2000s, maybe mid-2000s, where we started to hit the speed wall. We couldn't make our processors faster, so you see all these Core 2 whatevers. You started adding a bunch of cores, and that's how you still got that same transistor count increase. And nowadays, we have billions of transistors in our chips. It's a long way from, you have 32 core things. That's a long jump from like 5,000 transistors in the very first processors. Okay, so this is a line, so it's shown that we're still following Moore's law, still doubling the amount, but we're soon getting close to a flat line, unfortunately. So yeah, that is Moore's law in a nutshell. Computers are about getting double the amount of transistors every 2 years, and that used to translate to speed, but now it's translating to, we're just going to put more cores in our computers. Now we have like 16 core computers that are common. Okay, any questions, ideas about that? So yeah, the faster you can make your computers, the faster they can think and pretend to be humans and do cool machine learning stuff. And so that is what leads us to artificial intelligence and why it's become more popular these days. Like ChatGPT, for example, would not be working out if we only had tiny CPUs that didn't run very fast, right? So yeah, let's talk about artificial intelligence now, which is the idea of like making computers think, giving them artificial brains potentially, and we'll talk about how good they have become. And they're getting pretty good. Let me tell you. So yeah, let's talk about artificial intelligence. Let's just define it. I'll show you some cool examples. I'll let you play around with some stuff if you have never tried it before, and we'll go from there. So yeah, artificial intelligence in a nutshell is just when you teach a machine to think, to do some kind of reasoning. And so maybe you make a robot, for example, and you give it a bunch of sensors. And so artificial intelligence, one branch of it involves like making your machines perceive their environment in some way, like they have a webcam, or they have a heat sensor, or like a gyroscope or something. And they are in their programming, so they perceive their environment. They are able to make choices on their own, like move this robotic limb or something to achieve their goals, whatever you defined their goals to be. So they're maximizing some mathematical function that tells them how good of a thing their proposed activity is, I guess. And so this is a very utilitarian idea. So artificial intelligence is meant to help everybody achieve greater utility. And there's a bunch of subfields of artificial intelligence, AI for short. You have, of course, your robotics, and so maybe you've seen the cute little Christmas videos of these weird-looking robots dancing and doing flips and things. So that's one way to do it. Like, these all have sensors. They are, like, visualizing their environment in some sort of mechanical way and, like, achieving their goals of, like, getting to the other corner of the row or, like, lifting something heavy, things like that. Okay, so there's robotics. There's also machine learning. I would consider that to be a subfield of artificial intelligence. So, like, you got your face recognition, like, you have your chatbots and things that we have these days. All that fun artificial machine learning stuff, like it's drawing beautiful artwork for you. And the bulk of machine learning these days is done via neural networks, which is a model of a brain, a interesting computational model of a brain, like you talk about the individual neurons and you link them up in a programmatic way. So we'll get into that. And then, yeah, a lot of artificial intelligence is like, how do we achieve our goals? We have some mathematical function that we're trying to optimize. So secretly, honestly, artificial intelligence is just glorified statistics at the end of the day. Even machine learning, just glorified statistics. It's just a fancy buzzword for stats. Okay? So if you know stats, you could like break into the artificial intelligence field and do cool stuff. So yeah, with that, let me just show you some cool examples of artificial intelligence, show you how it works, and then I'll have you play around too, if you've never gone to some websites. I'll show you some cool ones. So here are some fun examples of AI. So the first maybe major example I would say of AI, maybe we're a little too young to remember, but the coolest new thing in digital cameras of the mid-2000s was blink detection. Maybe we've seen that, and like drawing boxes around faces to discover, hey, did that person blink or not? And then it'll like warn you and say you should take it again, right? So yeah, blink detection is machine learning, and what it's doing is it's able to find a head. It's able to find that, like, here's your digital camera, like you're taking a portrait of somebody. Here they are. It's able to notice where their head is, and inside of that, it's able to find where the eyes are. Like, it's trying to figure out, hey, are their eyes open? And so it draws boxes around them, like virtual boxes, of course, figuring out where they are based on where the head is and determining whether the eyes are open or not. And so that is a machine learning technique, just the ability to determine all that stuff. So it was programmed, the machine was programmed to do this somehow, and it's able to, with high accuracy, determine whether someone was blinking. And so I should, I guess, give you a hint as to how this really works. And that would help, I guess. It's a very popular topic. I'm glad I get to tell you a little bit about it. But here is essentially the nuts and bolts of how you make a machine learning program, how you make the blink detection, how you make ChatGPT, whatever, how you make stable diffusion, whatever those cool things are these days. So what you do is, it's essentially 3 steps. 3 steps because you're building something, you're asking a computer to learn something, and you're asking it to use the product of its learning on the future, okay? So step 1 usually is you make a giant conglomeration of knowledge that you will train your machine learning program on. It's called training data. So you're going to make a huge set of training data, and maybe, for example, we are going to train a machine learning model, we say, to determine whether somebody blinked or not. And so what we're going to do is we're going to make a huge set of training data with a bunch of pictures of people with their eyes open, right? A bunch of pictures of people with their eyes open. Maybe we draw a box around that so they can learn. But we're going to make we're going to give it a bunch of pictures, right? Because it's trying to learn to differentiate blinks from non-blinks. So we're going to give a bunch of pictures of people with their eyes open. Oops. And it needs to have pictures of people blinking as well, so pictures when their eyes are closed. And we're talking millions of these to get a good model. So that's essentially it. And then we do that. So we get a bunch of training data. This is usually the hardest part. All right. So there's that. And you're going to label it with what you want it to be like. All of these pictures with eyes open say that everyone everybody's eyes are open in this picture. Everything's fine. In the pictures where there's blinking, you should model that. You should label that picture and say, hey, computer, you better figure out that this person's blinking in this picture, okay? And yeah, so like, for example, like we're trying to notice faces, so we need to give it a bunch of labeled pictures with faces, eyes open, eyes closed, and then we should also just throw it some weird pictures too, because we don't want it to always try to find a face, right? Maybe in a cloud or something. We want to give it pictures of faces as well as pictures of non-faces, like planes or something, so that it doesn't accidentally think that the plane is blinking or something, right? So you need to give it a bunch of this data, as much as you possibly can, and that's the start. And then you ask the machine learning model to learn from that training data, right? So we train our model, we say, using some machine learning technique. There are a bunch of different ones. There are neural networks, that's the hot one these days, but there's plenty more. There's like decision trees, there's just normal logistical regression, which is just a statistics technique. But you give it to some technique, and it will get better over time. It will train itself on this training data. Figure out and try and like produce the label, like eyes open, eyes closed, or no, there's no faces at all. Stuff like that. Okay, does that make any sense at all? Any questions about that so far? It's a bit of a complicated idea, okay? But yeah, usually like you give a random model, one that's not trained at all at the start, and so it's like predicting random things, and it's horrible the first time you try it, but you keep giving it the training data over and over, and it slowly but surely starts improving its guesses, and it starts being more accurate on your training data over and over. Keep giving it until it improves. And eventually you're done. You give it as much time as you can give it. And at that point, you want to test it, because you've given a bunch of training data. It's slowly starting to get it right on the training data. The model is getting correct. What you need to do finally is to test it on a separate set of labeled data that you have not, like, this is like the exam time. This is the final exam for the model. You give it some data that you have not trained it on, because you want to make sure that it's not memorizing the answers, right? You want to make sure you give it new faces. It's still noticing. It's understanding the essence of what eyes are and what faces are, okay? And so you want to make sure on the separate set of data that you haven't told it about before that it's still getting everything right, and that confirms that it's not memorizing things. That's called overfitting. It's a very common problem in machine learning. But once you have a good result on this separate training, like testing stage, you can start putting that in cameras, because now you have some confidence that your program, your machine learning model, is correctly determining what faces are, what the differences are, when they're blinking, when they're not blinking. Okay, so that's machine learning in a nutshell. Neural networks, for example, they look like this. They're a bunch of artificial neurons. And so there's just a bunch of circles with lines, because this is what neurons look like in your brain. And they're passing information. They're linked in some certain way. And inside of a computer, inside of a neural network, what they are they're just a bunch of circles that are neurons with a bunch of numbers attached to them. Like this one has importance 1.0. That's its weight. This has weight 2.0. This has weight negative 5.5. Like this neuron is not helpful. It's inversely helpful. And then this one is like 3.3 or something. So you're like feeding in numbers, and you are sending these numbers along, and somehow you end up with a final answer. You end up with some final number that represents, like maybe if it's between 1 and 2, the eyes were open. Between 2 and 3, the eyes were closed. Between 3 and 4, it was not a face at all. So this kind of numerical input and output is what your computer machine learning model sees, and then maybe it's like this is supposed to be interpreted as a face with the eyes open, everything is fine. Okay, so it's just a bunch of numbers being shuffled along. That's all a neural network is, and there's a bunch of links. Like this number, like the original number was 1, and like this, it's becoming 2, it's becoming negative 5.5 somehow, and so there's weights along the arrows and things like that. But that's machine learning in a nutshell. Any questions about that? It is very complicated. This is like the topic of several semesters of knowledge. I could not give it all to you, but that's a good start, I think. And step 1, by far the hardest thing to do. You need to get a bunch of labeled data, and that is so hard to come by these days. But once you have enough, just give that to a neural network with enough time. It will It will figure out what a face is, what an airplane is, all that kind of stuff. And so this is why, if you ever use Google Photos, you have a Google Photos account, this is why Google Photos used to be free. Because they were, like, you were labeling your photos for your own purposes, and they were using that to train their machine learning models. And now they've got enough training data, so now you have to pay for it. So yeah, that's machine learning in a nutshell. I would like to show you the fruits of the labor of the machine learning scientists. If you have not seen this before, please go here. This is called crayon.com, C-R-A-I, with AI inside of it, of course. And this is like that stable diffusion idea, if you've seen that on the internet. It's like you give it a prompt, it will use machine learning, it will use neural networks to draw whatever you tell it to draw. Okay, so it's called crayon.com with AI inside of it, AI, C-R-A-I-Y-O-N, and you give it a little prompt, say what do you want it to generate, like, I don't know, a cat sniffing a flower with a rainbow in the background. Something weird, and it will just figure it out. It will take this prompt, it has a way of converting that to numbers, because it's a neural network, it's just shuffling around numbers at the end of the day, and then it will somehow determine the meaning of that sentence and translate it into more numbers, which will be pixels on an image. So take a couple minutes to play around with this, give it some things. It takes a while to draw because it's running on supercomputers in the cloud somewhere, but we're lucky enough to get it for free. Feel free to post on Discord the cool stuff that you build. But it takes about a minute, it says, and then usually it gives you a bunch of options. Like it tries a bunch of different ways of doing this. And look at how cute! These are weird looking. This is like a cat with one eye, a cyclops cat. But it's more or less like it knows what a cat is. It knows what sniffing a flower means. It knows what a rainbow is. It knows what the background is. It's able to parse all of that and translate it somehow to pixels in an image. It looks a little weird because, I mean, this is for free. It wasn't trained for as long as the commercial models were. But this is more or less the right answer, and this is like, you can click on it to expand it. Like, that is amazing, right? And you can tell it to draw like a certain person, and that's why it's like this is becoming very, very controversial, because it's kind of stealing people's art styles, and there are lawsuits in place on all of that. But look at these cute pictures of things that are almost cats and flowers, and then the grass. It's just beautiful. So yeah, hopefully you've got a couple prompts in while I was talking about it. But yeah, it's able to parse the text, convert it to pixels. Artificial brain. It's awesome. Okay, so it really is just doing this. Just got a giant set of these things called neurons passing weights along, and the output weights are just pixel colors, essentially. Any questions about any of that? That's my first example for us. And then my second example for us is more like real neural networks, like understanding what they really do. So like this picture again. It's called playground.tensorflow.org. I'd like you to go there, please. Playground.tensorflow.org. And it has a nice little place where you can play around with these things called neural networks. And so here is, on the left, you get to choose what your training data is. And the goal of this model, this virtual model that we're making, this example thing, is to separate the orange dots from the blue dots. So you can pick any of them. Maybe I'll pick this one. And here are your inputs on the left. These are the inputs to your model. And so you are given as data the points, right? You're given the 2D point coordinates of the orange dots and the blue dots, but you don't know. You're trying to train a model to predict whether they're blue or orange. And let me try and explain these as best as I can. X1 is the x coordinate of the dots. X2, for weird linear algebra reasons, is the y coordinate of the dots. And then this is x1 squared, so the x coordinate squared. This is x2 squared, so the y coordinate squared. These are x1, this is x and y multiplied together, And then you have the sign of the X and the sign of the Y. That might be helpful for some of the things, but you can give as many inputs as you would like to this neural network. And then you can have individual things called hidden layers. The output layer is at the very right, but you can make very long chains of neural networks here. And it's just passing along the information. Like it's passing along the coordinates, and it will learn little weights. Those are what the arrows are. Like the current random weight is all these things. You can kind of see how dark it is. And then the output is trying to predict whether or not it was like an orange dot or a blue dot based on the input information. So it's just learning the weights based on the training data and hopefully predicting whether or not the dot was blue or orange. And so essentially it's predicting a number. Maybe if the number is between 0 and 0.5, we consider it to be a blue dot. If the number is between 0.5 and 1, we consider it to be an orange dot. Something like that. So that's the kind of thing we're learning. And that's what machine learning is all about. Just come up with a number that represents what you're trying to represent. And so if you press play and play around with this, it will eventually learn something about this information. And you can see it like getting better. It's trying a bunch of options. You can see like these are the generations of the model learning things. And you can see now it has learned to classify the difference between, you can press pause when you're finished with it. You can see that it has learned to tell the difference between the blue section and the orange section. It knows what's in between is blue, what's outside is orange. And so, yeah, try just clicking some random things, playing around, and I'll show you a hint after that. Because there is a way to do it with the minimum amount. Like, I think you can imagine a smaller network, faster to train, faster to program, less money. And so you want the smallest network that does the right thing. And so I'll show you the secrets in just a second. But my goal to you is for these data sets, try and get the smallest neural network to differentiate between the orange and blue dots. And you press play to have it start learning. And so you have inputs, which are numbers. Coordinates are some mathematical function applied to the coordinates. And then these hidden layers, these individual layers in between that provide more information. Like they're able to remember stuff. It's like it's remembering combinations of the X and Y, which are lines, essentially. And we'll talk about that. But yeah, take a couple minutes to play around. Ask me questions if you have any. But this is neural networks in a nutshell. It's just you give it some inputs, whatever they are. You give it some training data, like the orange and blue dots, and it learns how to, like, where the orange dots were, where the blue dots were. And it becomes confident, hopefully, if you did it right. Well, while you're trying, I should say there's one secret that I could tell you now that might help you. Can I copy most of this? The way that it shuffles around these numbers, I should say, is it's just essentially adding them together, more or less, and then doing something to them. So if you give it, oh gosh, never mind. I'll just draw it then. If you have some inputs to your neural network and like it's shoving stuff around, let's see here. What it does is, if these all share to each other, there are, like this is a number 1.0, 2.0. It's setting this one, this next number, this next neuron, to be some combination of the previous ones that are feeding into it. Like this one's just going to be 2.0, some function on top of 2.0. And then this one is some combination, some function on like the sum of the 1.0 and 2.0. And so it's computing some answer, maybe like bringing it back down, and you just feed it in that way. So that's kind of my hint to you, like, what do you need? Like, what do you want to learn to differentiate the blue dots from the orange dots in this example? You want to learn a circle, right? So what's the equation for a circle? It's x squared plus y squared equals some radius squared. So it just needs to learn the radius. here is the x squared input, here's the y squared input. I don't even need any hidden layers because it will add them together, right? It'll add them together in the final neuron and learn a circle. See that? Immediately, it learns that circle. And so that's how you save money when you're a machine learning engineer. Any questions about that idea? That's the secret. You want to think about what you're learning. But at the end of the day, you can just throw a bunch of neurons at something and it will learn it. It always will work, which is a beautiful idea. And so what is this? Orange dots and blue dots in like the different quadrants. If you think about this long enough, it's about the sign. What's the difference? Like, how do you differentiate these dots? It's the first and the third quadrant there. When you multiply the x and the y together, you get positive, right? So negative times a negative is still positive. But in these other two quadrants, you have a negative coordinate times a positive coordinate. So the answer is negative still. And so all you need is this one input of multiply the coordinates by each other, and that will learn with very high accuracy. Loss is the opposite of accuracy, right? That's very, very accurate. That idea, like how to differentiate the corners of a graph, kind of. These two chunks, you can separate them with a line. So it's easy to learn a line by adding an x and y, like x squared plus x plus y equals something, like y equals mx plus b, kind of. So again, I don't need any hidden layers to learn that line that separates them. That's pretty cool. And finally, the swirl. You can't really make the swirl with any combination. Like the equation for a spiral is some weird thing involving like probably sines, but not these exact signs. And so the way to learn anything is you just give it a bunch of hidden layers. Just give it a bunch of neurons. It can memorize things. It can memorize weird combinations of those inputs. You see how it's kind of drawing what all that means. And so if you give it enough, and obviously it's slower to train now, but if you give it enough neurons, it'll figure it out one way or another, and it will get more or less accurate. Right now it's like still not figured it out quite. It's like half accurate. It's just guessing at this point, but you see how it's, okay, it's getting better, it's getting better, it's getting better. It's learning the spiral, slowly but surely. Isn't that cool? So it's learning a very complex mathematical function to describe exactly what's going on here. And if I let this run, you can see how it's getting slightly better and better and better over time. And if I gave this enough hidden layers, it would eventually get it. Probably it got it faster on your machines because you have these powerful computers in front of you. But yeah, that is the idea. You can learn anything with a neural network, and that's what makes them so powerful. That's why they can draw pictures and chat with you, things like that. Any questions about any of that? Just a fun example. Please play around with it. Ooh, there it goes. It's learning. It's getting better. And so, yeah, it's going to take a few generations, but it'll figure it out one way or another. All right. So with that, let's keep on trucking. Just a few more things to talk about. But those are fun examples. Definitely go back to them. Play around with it. So let's talk about maybe some potential issues with artificial intelligence. So we have like factory robots that build cars these days, right? Because machines are very good at doing something very precisely, right? You can write a machine, or you can make hardware and software that tells this machine to like turn its little machine arm by 5 degrees exactly. You can't get a human to do that very well, right? But the machine can do it just fine. It can do it over and over again very well, all right? Very hard to fail, can work all night long if you want it to. So sadly, these are taking over humans' jobs. That's one thing to worry about, because these robots can work faster than a human, much more precise than a human. That's unfortunate. But they do cost a lot of money, but you are saving that in terms of paying a bunch of people to do the same thing. So there's a tug and pull there. And so robots are taking over some industry jobs because of that. They're so good at what they do, better than a human. Unfortunate. In terms of just AI, artificial intelligence, maybe you think of that in terms of like general knowledge. And so a good example of this is the Watson device that was on Jeopardy a while back. If you remember that, there's a cool video that you can watch if you'd like. But let me talk about Watson, because that's a very good answer, or a very good example of just general artificial intelligence, the way that we think of it probably. Like, this is what an intelligent computer should be. It should be able to understand text and come up with an answer to your questions. Right? So what Watson did back in the day was it used what's called natural language processing. That's a subfield of artificial intelligence, natural language processing, to break down those questions on the Jeopardy game and answer them based on what it had stored inside of itself. It saved all of Wikipedia, for example, every news article that was ever written, stuff like that. And so when it went on Jeopardy, it just had a big hard drive with Wikipedia, all that other stuff. But what it did is it broke down the question into like a subject and a verb, and then it tried to figure out what the answer was probably. And what machine learning is all about is it's coming with numbers. And so it's like, usually it's going to come up with a bunch of different answers. That's what Watson did. It's like, all right, I think it might be answer 1 with a probability of like 10%. I think it might be answer 2 with a probability of 85%. I think it might be answer 3 with a probability of like 5% or something like that. And it would choose, if it's above some certain threshold, it'll be like, all right, this is my answer, I'll give that response. Otherwise, it'll keep its mouth shut or something. That's essentially what natural language processing is. It broke down the question and figured out what it was asking and used its knowledge stored inside of it to come up with likely options, and then it weighted those, and it gave back the answer that it thought was most correct. And that was, eventually, it started beating the humans, which is fun. And so, yeah, it went on Jeopardy, and you can watch it, like, just in the blink of an eye. Once it sees the question, immediately process it, come up with the answer much faster than the human could even hit the button. So, yeah, that is Watson. Have we seen that? Any questions, comments about that one? It's a fun video to watch. I encourage you to do it. But, yeah, I just have 2 more slides for us for the day. Let's talk about another very common example that's mostly known by, I think, a lot of us. Computers playing games. Probably the most popular ones are chess and Go, but it was a huge thing back in the late 90s when a computer finally beat a chess world champion. So computers had gotten strong enough to beat grandmasters, or whatever the chess equivalent of like the smartest chess player is. And it beat this man, and like the world was abuzz, and it was wonderful. More recently, and there's a video for that if you want to watch it, there's the game Go, which is a board game that is a bit more complicated than chess, and so it took longer for computers to get good at it and beat humans, but they finally did back in 2017, beat a world champion at a tournament of the game Go, and yeah, it's just crazy what it did. But the reason these games are so easy for computers to learn and get good at is because it's very easy to say like what you can do, the moves you can make, and it's very easy to say when the game is over. You can write all those into a program very quickly, and then you can take your model, right, and you can just have it play itself, because they can all just make random moves and slowly learn technique, right? Because the rules of these games are so like set in stone, so clear, there's no room for guesswork. You can just have the computers play each other. You can have the machine learning model play itself for more times than any human could ever play chess, like millions of times, lifetimes of chess games. A computer can run in the blink of an eye against itself. And that's what makes it so strong. And so this is what happened. This is how you make a machine learning model play chess. Like, you give it a blank game board, and then you tell it to make a move. And it's just going to try all these possibilities. It's like, all right, I'm going to play a game where I move this way. I'm going to play a game where I move this way. I'm going to play a game where I move this way. I'm going to play a game where I move this way. Things like that. And it can learn what the best options are, because it can kind of like model how the game is going to get played. Like, if I make this move, here are the possibilities of my opponent making these moves. All these possibilities after my move. And so it can play the game a bunch of levels deep for all these different options. And it can be like, all right, this one is going to give me the best chance of winning. Like, the opponent can't really beat my move as good as they could in the other ways. So I'm going to pick this one instead. So there's a mathematical game being played here. It's just a bunch of numbers. Like, what's the strongest move for me? Because it can think so far ahead, and it can also play itself. So yeah, it can learn the rules. It can learn all the fancy openings, even though it doesn't know the names. Any questions about that? It's just a fun idea, I think. But it's powerful because, like, you have unlimited training data for your machine learning model. All those words we just talked about. If you have a game like this and you can have it play itself. Isn't that beautiful? Any questions, comments about that? All right. So yeah, the last thing that I want to say for the day is give us just an example for our essay, because I know we're trying to scour the internet for random fallacies, because people are wrong all the time. And so here is a good example that I stole a couple years ago. And it's, I guess, kind of relevant because it was just recently International Women's Day this year. So here was a tweet by the vice president. And this is an example of a straw man fallacy. This is the kind of thing I want you to do. Oops. Don't do that. There we go. This is an example of a straw man fallacy. And I guess I'll move my zoom up here or something. There you go. Go away, zoom. This is a straw man fallacy in response to this tweet, and I'll try to explain it in the way that I want you to explain it in your essay. So like you make a paragraph about this particular example. So like, here was the fallacy. On this International Women's Day, I want to honor the women who for over a year have gone to work. This was during the pandemic, of course, and so this is the vice president tweeting about this, just to celebrate International Women's Day. Gone to work, often risking their health to nourish and protect us, doctors, nurses, teachers, all these people that she wanted to like pay tribute to. And then this person replied to this tweet with a straw man fallacy. And so let me try to explain it. So you'd like set the scene in your essay, but here's the tweet. Just the women. Guess that would be typical of you. I thank all who risked life for others. And so this is a good example of a straw man fallacy, because this response is putting words into the vice president's mouth. I have no reason to believe that the vice president only wants to thank women. Like, she does not want to ever thank any male doctors, any male nurses, because that is exactly what this reply is saying, right? Do you see how this person is putting words into the vice president's mouth? That's a straw man fallacy. The vice president is not saying anything about not thanking men. She's just trying to highlight, because it's International Women's Day, the work of women, right? And so this is exactly what you would do in your essay. You'd be like, all right, here's the scene. Here's me quoting these tweets. Here's this response. This is a straw man fallacy. So you say its name. This is a straw man fallacy because this person is putting words into the vice president's mouth. The vice president is saying nothing about men, right? She's not trying to rag on men, to say anything bad about men, or say that they should not be thanked. She's just trying to spread awareness for International Women's Day, give her thanks, things like that. And that is not at all what this is trying to argue against something that she didn't even say. Okay, does that make sense? So that's how you would analyze the things that you find, and believe me, there's plenty of them. So yeah, I think that is all that I wanted to say about that. Any questions? Hopefully you've found a few already. But are we good? Any last things we want to talk about? Yeah, I think that is where I want to stop for the day. We'll come back here more and do fun artificial intelligence things next time. Let's see, is there any assignments to give out? I believe that was it. So yeah, that's all for us for the day. The rest of the time is yours to work and find some fallacies, I guess.